Good morning, students. We are going to discuss the same topic that we discussed yesterday, but this is probably the last time we are having a discussion on it, because after this we'll move on to something different. So for one last time, I have selected a few questions for discussion. So you know those rules that we have just discussed in the last lecture, the rules for calculating uncertainty in the final answer when we have measured many quantities. For example, I have measured voltage, I have measured current. Now I want to calculate the power dissipated in that resistance R. For making use of the appropriate relationship, this could be R is equal to V over I. This could be power is equal to V into I, or any other useful relation that is given. It could be two values given. Let's say they have given us the value of voltage, and that is 4.8 plus minus 0.2 volt. And another quantity that is measured and that is provided, that is resistance of a particular resistor, and that is 100 ohm. But this time, instead of giving it in the form of absolute uncertainty, they inform us that there is 5% uncertainty in the quantity, which is the resistance of a certain resistor. So this is something you should note, because sometimes they express the uncertainty in the form of percentage. This is in fact easier when uncertainties are given in the form of percentage, because when we express this as well in percentage, it will be easy to find the power expressed in the form of percentages of uncertainties in these quantities. Let's say this is the relationship that we are going to use, V square over R. If instead of resistance we had current here, then of course the relationship would be V into I. But instead of current, we are given resistance, so V square over R is the proper equation that is to be used in this case. Before we attempt this, we need to calculate the percentage uncertainty in the value of V as well. Why? Because we can express all these quantities in this manner. This is the total percentage uncertainty in the quantity labeled P here. This is delta P over P. This should be equal to 2 times the percentage uncertainty in the value of V, which is this. This is the percentage uncertainty in V, and this 2 has come from this square. This is the last rule we discussed yesterday, that whenever there is a power appearing in a formula, we use that power as a product of the percentage uncertainty in that quantity before it is added to the percentage uncertainties of the other quantities. Like I'm adding it to the percentage uncertainty of R now. So delta R over R into 100. This is something we already know, and this is the quantity which is given at the start of the question. So 5% means all this. So this number is 5. I can write 5%, but 5 is basically the number that we can add to whatever we are going to have here. So let's see what is this percentage uncertainty in this quantity. Obviously, this is calculated like 0.2 divided by 4.8 into 100. And this is 2 into this percentage uncertainty comes out to be 4.2. This is 4.2. When this 4.2 is multiplied to this and then added to 5, we have the total percentage uncertainty in the value of power dissipated. So this is 8.4 plus 5, which can be easily worked out to be 13.4%. That means the total percentage uncertainty in this quantity is 13.4%. Why? Because I know the percentage uncertainty in the value of R, and I know the percentage uncertainty in the value of V multiplied by 2 because of the formula. So all this adds up to this. That means even if you don't have to change it and simply percentage uncertainties are given, like this is 5% and this is 4.2% already given, you will just write them as an addition here. So percentage uncertainty simply add. If there is no power, obviously there is no need to multiply it by any number, but if there is some power, you use this as a product. So the last thing is how we calculate this delta P now, the actual uncertainty in the value of power. So obviously for that purpose, we need to know what is the value of P. The value of P is calculated using this formula. So V square over R. V square over R means V is 4.8 square divided by this 100. The value of R is in ohms, so this is 100. Whatever this number is, we use this number to calculate delta P, and therefore delta P comes out to be 13.4, which is this number, the total percentage uncertainty, divided by 100 multiplied by P, which means 4.8 squared divided by 100. So this is our final answer of delta P. I assume, I have not done this calculation, but let's assume this is this number is something like 4.8 into 10 raised power minus 4. Suppose this is in watts, delta P, and the value of P, let's say it comes out to be something like sorry, this is the value of P, 4.8 into 10 raised power minus 4. I'm assuming because the value is slightly different, but I'm going to give you an idea of the final rule here, which you will take care of to write this answer in its proper form. So there is a point or two at the end that you need to keep in your mind. Delta P is something like 0.68 into 10 raised power minus 4, which was a step before. It was 6.8 into 10 raised power minus 5. It was something like this. The value of power is this and delta P is this. Now the last step is, how do you write the value of P and its actual uncertainty in its SI units? This is usually the last part of the question in which you have done all these calculations, and now you are required to write this answer plus minus this, so they know that you understand how to make that final adjustment. Sometimes you have to make some adjustment here, sometimes you have to ignore a digit or two, so there is a consistency of significant figures. So this is the point that I need to elaborate on. That's why we are talking about this. So power is 4.8 into 10 to the power minus 4 watt. And this delta P, the uncertainty, is 6.8 into 10 to the power minus 5. So the first thing is, I need to make this and this same. When I make these two same, there will be a convenience, like this is 4.8 plus minus 0.68 and all this into 10 to the power minus 4 now. But there is one more thing to be considered, and that is this delta P cannot have more than two significant figures. When we say significant figures, that will mean after decimal there should be just one non-zero digit, and that non-zero digit should be after several zeros. That is possible because the zeros before any non-zero digit are not significant. So 0.01 means one significant figure. 0.00001 is again one significant figure, although there are several zeros before the decimal, after the decimal. So in the final answer, the adjustment that I was talking about is that in the final answer, I will write this as 4.8, of course, but this will be changed into 0.7. And this is simply the rounding off rule at work here. And this 10 to the power minus 4 will be written as it is. So this is how you write your final answer. Let me write this clearly here. I repeat that I'm assuming these are the answers to P and delta P. The answers could be different, but I'm just elaborating on the rules that you need to consider here. So if you have a value of P and plus minus delta P, the final answer is written in this way, 0.7. And this 10 to the power minus 4 is common to both with the unit which is same for the two. This is possible that you write 4.8 into 10 to the power minus 4 plus minus 0.7 into 10 to the power minus 4. This is okay, but this is more logical, and this makes more sense that you write this as a factor of these two with this sign in between. So 4.8 plus minus 0.7 clearly shows what is the main the number of significant figure in this are 2, and in this significant figures are 1. So the important rule is that whatever number of significant figures you have here, at least there should be a consistency in the number of digits you have to the right of the decimal. If you have one digit to the right of this decimal, there should be one digit immediately after this decimal. But you cannot have more than one significant figures here. If it is 0.07, that is okay, but 0.07 doesn't fit here because it is 4.8 and nothing after. So if it is 0.07, you must add one more digit here that you found during the calculation. So you consider the third significant figure here as well. Let me give an example to that effect in the next question. In the next question, which is about a cylinder, a figure like this, and its diameter is given, and its diameter is given to be diameter is to be found. Its length is given. The length is given to be 10 centimeters, and its volume is given. So if length is known to be 10 plus minus 0.1 centimeter, and its volume is also given, and that is 50 plus minus 0.5 centimeter cube. And the relationship which relates the diameter and the length to the volume is pi d square L over 4. This is a familiar formula. You have been learning and using this formula for many years since the early classes. So pi d square, this could be pi r square L basically, but when you replace r by the diameter, it becomes d over 2 square, so that is d square over 4. So this formula is used to determine the value of diameter and the uncertainty in it. The question is, what is the diameter equal to, and what is the uncertainty in it in centimeters? So this is the question. Again, looking at this formula, if we rearrange, this D becomes 4 times volume over pi into L. So this formula could be used to determine the uncertainty in the value of D first. So delta D over D is equal to delta V over V plus delta L over L. There are no powers involved, and there are two constants which are simply ignored because there are no uncertainties in any constants given there. So V over L, which is the quotient of two quantities, and we are following the same rule, which is rule number 3, which tells us that total fractional uncertainty in this quantity, which is on one side, must be equal to the sum of all the fractional uncertainties which are given. Like L, the length is given, the volume is given. So the next step is that we quickly calculate the total fractional uncertainty on this side, and that will of course be equal to the fractional uncertainty in the value of diameter. So delta V over V, which means 0.5 over 50, 0.5 over 50 plus delta L over L, 0.1 over 10. We simplify this, and one thing that I ignored here, and I must have considered, it was D square here. So because it was D square, I must have taken a root of this side. That means we have powers involved here. So if if I consider this 4 under root as 2, this v under root means 1 over 2 power, this pi under root is constant, and this L is 1 over 2. So there are powers involved here and both are 1 over 2. So I take 1 over 2 as common in the two. Due to this square, when I made this d as a subject of this equation, I should have taken root on this side. So this was an omission, and you need to take care of these things in actual questions. So power is 1 over 2. Both of these quantities are 1 over 2 power. So whatever number I have here, I'll multiply it by 2. So this all simplifies to, when I simplify this all, it comes out to be 2.52 centimeters. Sorry, this is delta D. This is delta D over D, and this comes out to be 0.01. All this simplifies to this number, 0.01. This is delta D over D. Now, in order to find out the value of delta D, the uncertainty, the actual uncertainty in D, obviously we need to multiply this 0.01 by the quantity here, the actual value of D that we have measured or we need to measure. So D is calculated from this formula directly. So 4 times V, this is 50, divided by pi into L, yani 10. We use all these values here, 0.01 into 4 into 50 divided by 3.14 into 10, all this raised to the power 1 over 2, and when simplified, this delta D comes out to be 0.025. This is delta D. And now that same point that I discussed at the end of the last question, I'm going to discuss here again. So that will be the final form of the answer in which we write this D plus minus delta D. I am going to write answer to this one now. So how will you write D? Let's write D first. The D that I calculated directly from this formula, it came out to be 2.52. And plus minus 0.025. But this is not still the final answer, because there is one small problem in it. The problem is you have more than 2 non-zero digits here. So one rule is being violated here. That means I must change this into 1 digit. I have to make this into one significant figure. 25 can be rounded off to 30. That means I can write this as 0.03. This side is okay because 2.52, we have already 2 digits on the right hand side of this after decimal point, because there are 2 decimal places after this. So 0.03 means there should be 2 digits in this after decimal. If I had chosen in my calculation, I had chosen my answer to D as 2.5 only, then it would be a problem. I mean, this would be a problem. So unless I choose and retain this digit, which is 2 places after the decimal, there will not be a consistency between the significant figures. Now this is okay because we have one significant figure here, and there is consistency with the decimal places because we have 2 digits in this. So this is the final form in which we will write the answer. So this is all we have today for discussion. I have shared with you some questions. Yesterday we uploaded a worksheet. You try those questions. There will be another worksheet uploaded today, and it will contain questions like this. There could be challenging, but that is what this exam is about. Go through all this. If you have any difficulty, you can always let me know in the question answer sessions. Thank you for today.